Piecewise defined functions. Okay, so most of the functions we've been looking at so far are what we call smooth or continuous. Or like we've seen, you just have, an input and an output, one equation. However, we're going to look at piecewise defined functions. So now that the term smooth is an actual mathematical term, and that means no sharp turns or jagged edges. That's not, a very mathematical definition, but it'll do well enough for us for now. If you move on to calculus, you'll get more into that. Also, continuous means that you can draw the entire graph without lifting your pencil. And again, that's not a very mathematical definition, but it's good enough for us now. So let me give an example. Okay, so an example is something smooth and continuous is, the kind of stuff we've seen. So if we have some kind of, input, output thing going, smooth and continuous, got to make sure I'm on the screen here, is, just something like that. Smooth, continuous. There's no sharp turns, no jagged edges, and I can draw the whole thing without lifting my pencil. So what's an example of something not smooth and continuous? Not smooth and continuous. Kind of like this video. Anyway, so why is this not smooth and continuous? Well, so smooth means there's no sharp turns or jagged edges. So we've got a function here. It's coming along. Every input, there's only one output. But then right here, it's like, and it kind of is like jagged there. So here we'd say that's not smooth. Not smooth. And then we're going along, and then so we get to this value, then all of a sudden it takes a big dump. A big drop right here. And so this area in here is not continuous. Okay, it's still a function. It's just saying because of this kind of drop off, it's not continuous. There's no way I could have gotten from here and then jumped from here without lifting my pencil. So not continuous, not smooth. Okay, so now one of the hardest things with piecewise defined functions. A piecewise defined function is, used in mathematics and sciences and any kind of, you want to model something mathematically, and there's just no way you can do it with just one piece. So this is the notation we're going to use. And this is where students often get confused. Is if you can understand the notation, you'll realize, it's not as weird as I thought. So what we have is we have a large left brace. And so it'll look something like this. I'll just do an example. So we've got the function name. And so there we can either call it y or f of x. We can pretty much use those interchangeably. What do you want to use, y or f of x? Use f of x. All right, I will use f of x. So we'll call it f of x. We write it like that, equals. And then we've got this large left brace. Oh, come on, is that a good brace? That's not bad. Okay, and that's just showing, hey, we're going to collect a whole bunch of stuff that's going to be equal to this function. And so first, in our first column, we put the function pieces. And then in the next column, we put the domain of each piece. This would be good to take notes on. Am I on the screen? Yeah, staying on the screen. So remember, the domain is all the possible inputs. And so with a piecewise function, it's pretty important because when we put an input in, we want to know which function piece do we use. So for my example, we've got our function pieces. So I'm going to say x plus 3, I'm just making this up, for x is less than or equal to -1. And let's say the function output is 2 when the input is between -1 and 2. And let's say it's equal to x squared when x is greater than or equal to 2. And you're like, some people might be like, oh, that makes sense. Other people are like, oh, what the heck's going on? So let's take a look at an example of how we graph this. Okay, so to graph this, I'm going to get out some graph paper. What I would do, write this down so then you can refer back to it, because now I'm going to put on some graph paper. So if you remember, our first function piece was x plus 3. So what that means is f of x equals x plus 3. Or in other words, y equals x plus 3. And we all should be able to graph that. And now notice I'm using pencil. And I'm using pencil because I'm going to be doing a lot of erasing. So y equals x plus 3 means our y-intercept is 3 and our slope is 1. So we go up 1 over 1. And so we get a line that looks like this. And notice I'm writing it in really lightly. And I'll make it dark here in a second if you really can't see that. But now look back on our function. It's only x plus 3 for the domain where x is less than or equal to -1. So I go back to my graph, and I'm going to erase everything except for x is less than or equal to -1. So all this is going to stay, but all this is going to go bye-bye. I'm going to erase that. Now, can it equal -1? Yes, it can equal -1, so I'm going to make a filled in dot there. Now let's go back to our graph, or I mean our function. It says that f of x equals 2. Okay, so I'm going to draw that in. Remember, I'm using pencil because I'm going to erase. So remember, f of x equals 2. That's the same as y equals 2. And y equals 2 is a horizontal line at 2. So that's like this. Now, but look, this is where the domain part is important. That's only between -1 and 2. So only between -1 and 2. So it's only this part. So I'm going to erase the rest of that. Now, at 2, does it equal 2? No, it's less than 2. So we leave that as an open circle right there. Okay, now finally, we've got x squared. Y equals x squared. F of x equals x squared. So let's graph that. And so x squared looks like something like that. Okay, just sketching it. And then it's over here, but again. But again, this is why I use pencil, because it's only for x's greater than or equal to 2. So I'm going to erase all this, and that's obviously why I didn't draw it on very dark. It's because I knew I'm going to have to erase. It's only for x's greater than or equal to, so I fill in this mark and then continue it this way and put an arrow because it just keeps going. Keeps going forever. Okay, so where's my... So here is the graph of that piecewise defined function. Open circle there, and then it's y equals x squared, which is hard to sketch, but it goes off like that. And this is... So that's how you graph that. And the hardest part, I think, is realizing, what does this mean? You've got 3 different outputs based on what input you're using. So you need to check what input you're using. So let's take a little pause here. Pause, music done. Okay, so the pause is done. Here's a problem where we've got, say we were modeling something, and we found that this is what our graph ended up looking like. And we know that this first piece is, this is our function, and then the second piece, this is our function. And we're told that this is at the point 7. We are told to use the correct notation to write as a single piecewise defined function. So let me write out what we're doing. Bing! Write as a single piecewise defined function. So to do that, what do we want to call it? Let's call it f of x, y of x, f of x. Y of x, doesn't matter. We'll call it f of x. So f of x equals, and then we make our big brackety thing like that. And so we know it's equal to this thing. Negative, let's see if I can fit it in here. Negative 1 point, that's what she said. Negative 1.5 x minus 5 plus 10. But where does that happen? Well, that happens from right here, which is at the point 1. Less than, can it equal 1? Yes, less than or equal to x. And now let's see, does it equal this, or is it simply less than? It's simply less than because that's an open dot. So less than 7. And then it's equal to this other piece, negative square root of x minus 7 plus 5 for everything x is greater than 7. So that's for x is greater than, can it equal 7? Yes, because it's going to be this because it's the dark dot. So x is greater than or equal to 7. So that's how we use piecewise defined functions. So in this column here, this is our output in a sense. This is our what we do to the number. And this, when we plug in a number, so it's kind of weird because we sort of read right to left. And I'll show that in the next problem. But first, whenever we have an input, we have to look over here, which one does it apply to, and then we plug it in over here. And that'll be on the next example, and then we'll be done with this lesson. Okay, so here's a good example to see, are we understanding how to read a piecewise defined function in the notation? It says evaluate each piecewise defined function as indicated. So in other words, if we plug in a negative 3, what's our output? If we plug in this one, what's our output? If we plug in this, what's our output? So let's just go through h of negative 3. That means we plug in a negative 3. First thing we need to do is to figure out which of these outputs do we use. So we take negative 3 and we look. Negative 3 is less than 0. So that means we're going to use this one. So we go over here, and so it's going to be 2 times, we just plug in the negative 3 into the function that corresponds with the domain. 2 times negative 3 plus 3 equals negative 3. So that's our output. Let's do the next one. H of negative 3 over 2. Again, we look up here. Negative 3 over 2, that's going to be in this top one because that's less than 0. We plug that in, so we got 2 times negative 3 over 2 plus 3. And I think, what does that give us? That gives us an output of 0. Let's try the next one. H of negative 0.0001. So again, we've got to look up here. Which domain does that fall in to know which function to use? And so negative 0.001 is, we're still up in this one. We're less than 0. So we go 2 times negative 0.0001 plus 3. And I think if my calculations are right, that's going to give us 2.999. I think I added an extra 0. Oops. Yeah. So one more 0. 2.9998. Yeah, somewhere around there. Okay, you get the idea. Let's do the next one. H of 1. H of 1. So Again, we look up here. If we have an input of 1, which of these domains does it fall in? Then we go back over here. So if we look over here, 1 is going to be in this one here, because 1's between 0 and 2. So we use this to determine our output, the x squared plus 1. So h of 1 will be 1 squared plus 1. That equals 2. Let's try h of 2. So if we plug in a 2, which one of these output functions do we use? H of 2. So we look up here, 2, well, this one is only for values less than 2. Oh, they're being tricky, those little boop. This is only for values less than 2, and this is only for values greater than 2. So in fact, at exactly 2, we don't know what to do. So it's undefined. So 2 is not in the domain because it doesn't fit into any of these. So h of 2 is undefined. I think we got one more, h of 3. Oh, that's easy. So again, we look up here, h of 3. If we plug in a 3, 3 will fall into this third one because 3 is greater than 2. And then we go back, we go to the left, and that's where I think a lot of students get confused because we're just so used to when we read things, we go left to right. Here, you look in the right column first to see which one you use, and then you go back. And that's easy. So anytime we plug in something greater than 2, our output is always 5. So h of 3 is just 5. And hopefully that gives you a good idea of how piecewise defined functions work. Again, the hardest part is how do you read this? And so if you're still confused, go through this video again and realize you need to look at this column first to see which function to use. Hopefully that works. 17 minutes. Oh, it's too long. That's all right.